Unbalanced magnetic pole. A synchronous generator has a stator with a three-phase winding and a rotor with the permanent magnets. If the rotor is properly centered, then the total force acting on the rotor is zero. But if there is an eccentricity, then there is an uneven air gap which causes the unbalanced magnetic pole. Our task is to calculate the force acting on the rotor. I am going to reproduce the real case experiment. The machine is assembled. There is no current in the stator winding, and I will measure the force acting on the rotor when it is properly centered. Then I will move the rotor to one side and again measure the force. Okay, let's start QuickField now.
Generator. Next. Problem type is DC magnetics. Model class is plane parallel, length units are millimeters. The axial length of the generator is 130 millimeters. Finish. On the left you can see the problem pane, and on the right is the Geometer model editor window. You can draw the Geometer model here, or you can import the Geometer model from the AutoCAD.exe file. I already have the drawing prepared, so I will import the model. Here it is. Here you can recognize the stator, the rotor, the shaft, the slots with permanent magnets, the slots on the stator. And let's zoom in, and I will need the middle line in the air gap. So I'm going to insert a circle with a diameter of 183 millimeters. Insert. Close. Okay. Now let's assign labels. Through labels you can explain the geometric object's meaning and provide physical properties. Switch to Select Objects mode. Click the object to select and type in the label name here. This is stator. Click here. This is shaft. This is rotor yoke. And these parts are rotor steel. To select multiple objects at the same time, hold the Control button pressed. Rotor steel. There is no electric current in the stator winding, so there is no need to assign specific label to each slot. I'm going to select all slots and assign the same label to all slots. These are slots. Now let's zoom in. Switch to Select Objects mode. Click here. This is the air. And here is the air. We have the slots on the rotor, and in the slots there are permanent magnets. And the slots are closed with the wedge. So these wedges. Wedges. And inside the slot is the insulation. Insulation. Now let's assign labels to the permanent magnets. For example, this permanent magnet is located in the slot with angular position of 45 degrees. and the magnetization is directed here toward this pole. I'm going to give this block the label 45 plus 90 degrees. 45 plus 90 here. Okay. And this would be, let me check, 30 degrees is the angular position plus 90. This would be 15 degrees. 15 plus 90. And this would be 60 plus 90. And this would be 75. 75 plus 90. Okay. Now what about this magnet? Its position is 135 degrees and the magnetization direction is to the right and up, perpendicular to the slot vertical axis. For this block I gave label 138, which is this block position, minus 90. Minus 90. This would be 120 minus 90. So far these are just text labels. And these would be 105 minus 90. This would be 150 minus 90. And this would be 165 minus 90. Now let's move to the bottom part. This magnet is magnetized to the left and down. Again, the magnetization direction is perpendicular to the vertical axis of the magnet. The vertical axis is minus 45 degrees. So I give it the label minus 45 minus 90 to the left. This would be minus 30 minus 90. This would be minus 15 minus 90. This would be minus 60 minus 90. And this would be minus 75 minus 90. Now the last quarter. This magnet position is minus 135 degrees and it is magnetized to the right and down. So this is position plus, because to the right, plus 90. This magnet position is minus 150 plus 90. This is minus 165 plus 90. This is minus 120 plus 90. And this is minus 105 plus 90. Okay. Summary. We have labeled all blocks. Now I am going to assign label to the external boundary. Again, hold the Ctrl button pressed to select both arcs. External, and I'm going to give the label to the middle line in the air gap. Select objects, click to select air gap. Okay, now let's provide physical properties for these labels. Double-click the label name in the tree. Relative magnetic permeability of the air is 1. Okay. Relative magnetic permeability of the shaft is 1. For the slots, again I specify permeability of 1. For the wedges, I specify permeability of 1. For the rotor yoke, I specify permeability of 1. And for the rotor steel, I should specify the BH curve. I already have the data prepared. Here is the BH curve data in the text file. I simply copy this value and paste it here. Close, OK. And the stator is made of the same steel. So for the stator, I use the same BH curve data. OK. For the insulation, I specify magnetic permeability of 1. Now, what about the permanent magnets? They are all made of the same material with the magnetic permeability of 1.2 and the coercive force magnitude of 955 kiloamperes per meter, but the direction varies. For this permanent magnet, the direction is 45 plus 90. Okay. For this permanent magnet, the same permeability, the same magnitude of the coercive force, but the direction is minus 45 minus 90. And I keep on going and assign same magnitude of the coercive force and same value of the permeability to all other labels of the permanent magnets. Only the direction varies. Okay, I have provided physical properties for all blocks. Now, magnetic field is contained within the electric machine. There is no magnetic flux going outside. So for the external boundary, I specify zero magnetic potential. For the middle line, there are no specific properties to assign. So I do not specify any data here, just click OK. And you can see the zero mark next to the label name. That means it is an empty label that doesn't hold any physical data, and this label is simply ignored during the analysis. Okay, the geometry model and the data are ready. Before I start the analysis, I should build the finite element mesh. Just press this button, and the mesh will be generated. Now save all problem files and solve the problem. The problem is solved. Let's take a look at the results. Here you can see the magnetic field lines. Let's calculate the force acting on the rotor. I will use the contour tool. Click to select the rotor. In fact, I should also select the permanent magnets. So the faster way to select the rotor assembly would be to build the contour in the air gap. That's why I added the middle line in the air gap. Contour clear. Let's zoom in. contour, click to select the edge, click to select the second edge. Now the contour is closed, but it is directed clockwise. I should change the contour direction. Now the contour is directed counterclockwise and the rotor assembly is selected. Now I can calculate the volume integrals. Integrals, mechanical force. The mechanical force should be 0 because the model is symmetrical. I get the force 1.4 newtons, which is a pure calculation error. Okay, now let's move the rotor down by 1 millimeter. Open the Geometer model, select, again I should select the rotor that contains many parts. I better select the stator. Let's move the stator up by 1 millimeter. Let's zoom in. I should also move the middle line. Okay, let's first move the middle line. Move selection up by 0.5 millimeters. Now click to select the stator and move the stator up by 1 millimeter. Okay, now let's select everything and move it down by 1 millimeter. Now the stator is placed at the same position as it was, but the rotor is shifted down by 1 millimeter. You can see the A gap here is large, but the A gap here is small. And if you check these center point properties, you will see that the rotor is shifted down by 1 millimeter. Okay, let's again build the fine-tunement mesh, save all problem files, and solve the problem. The problem is solved. Let's take a look at the results. Again, I can see the field lines, and I cannot say that there is some change or asymmetry in the field picture, but let's calculate the force. Again, I will build the contour in the middle of the A gap, contour change direction, follow to the integrals, and here is the mechanical force. Now there is a force pointing down, and the force magnitude is 700 newtons. This force is calculated for the machine that has the axial length of 130 millimeters. I can see the magnetic flux distribution in the A gap. Open the XY plot and switch to the flux density normal component. Remember, we have an uneven A gap. At the top where the A gap is large, the flux density is low. And at the bottom part, when the A gap is small, the flux density is high. QuickField features a harmonic browser. Choose the value, flux density normal component, and you see the harmonics content of the flux density distribution. Remember, we have 4 poles here, so the unity harmonic has number 2, and this would be the 3rd harmonic.
If you search for the unbalanced magnetic pole on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.